Welcome to Hot Chips 20. Session 6, PC Chips.
First speaker, which is Niles Burbank. Niles has a long career with ATI and now AMD since their acquisition, designing some of the first 3D accelerators that ATI made. And today he's going to tell us about one of the latest and most advanced integrated GPUs.
Thanks, John. So I have the timer, I guess, start here momentarily.
I'm not quite sure how to get it going, but nope.
Okay, thank you. So as John said, I'm Niles Burbank. I'm from AMD's office in Markham, north of Toronto, formerly an ATI office prior to ATI's acquisition by AMD a couple of years ago. And it's my distinct pleasure today to give you a little bit more insight into our recently announced 780G IGP, or Integrated Graphics Processor. I'll start by just briefly describing the market conditions into which we introduced this product, because there's a lot of new demands that we're facing from our customers that created a number of design challenges for the product. I'll provide a little bit of an overview of the product, talk about the design challenges that those customer expectations created, and then I'll talk more specifically about some of the capabilities of the product in the areas of video playback, display capabilities, and power optimizations in particular. So just briefly, I think most of the audience will be familiar with this, but the PC market is one that's evolved in a way which has made the lives of semiconductor vendors significantly more challenging over the last several years, particularly in the area of mainstream PCs, where a low-cost or mainstream PC traditionally would have been used for a variety of fairly straightforward pedestrian tasks, email, productivity applications such as Microsoft Office or similar office suites, web browsing, and significantly energy consumption or power consumption was traditionally never a big consideration in the purchase of a desktop or fixed location PC. What's happening now, though, is all of those traditional assumptions are out the window. That people expect even a low-cost PC to be able to do content creation, creation and editing of videos to upload or share with their friends and colleagues, gaming, including some fairly advanced 3D gaming, playback of not only basic video but high-definition video, such as might be provided from Blu-ray, and significantly in our increasingly green-conscious society, energy consumption is becoming an important purchase consideration even for desktop PCs. And of course, given the long-term trends in the PC market, customers expect all of this at the same price point or preferably a lower price point. So it's into that environment that earlier this year we introduced our AMD 780G IGP, Integrated Graphics Processor. And what you'll see on this chart is on the right-hand side a picture of a typical PC motherboard with the 780G called out and its companion chip, the SB700 Southbridge. And the overall solution which we're offering to the customers consists of the 780G with its integrated graphics core, its video acceleration capabilities, the companion Southbridge chip, a processor, of course, and a variety of value-added software, notably our overdrive utility to allow customers who are so inclined to tune the performance of their system, and ATI's hybrid graphics capability to allow use of the integrated graphics functionality together with discrete graphics for additional performance than would be possible with either device on its own. So this slide simply shows a fairly simple diagram of how the 780 fits into the platform in terms of the overall platform architecture. You'll see it in the center of the diagram. Because of the fact that it does include graphics capability, we have to provide directly all the display outputs which the customer might require from the 780G itself. And that includes analog outputs such as a traditional VGA output, as well as a host of digital outputs. And again, because of the cost considerations that our customers have, those digital outputs need to come directly from our ASIC rather than through a translator chip, which would result in additional cost. In addition, the 780G is the connection point for high-speed I/O through the PCI Express bus in the chip, and that would be used to connect to optionally an external graphics accelerator or GPU, as well as to other PCI Express peripherals, and has an optional connection to what we term a display cache, which is a single piece of DDR2 memory, which can optionally be populated to provide additional performance and reduced power, and which I'll talk about a little bit more in a few minutes. Now at the system level, it's paired with the South Bridge, in this case the SB700, that provides a legacy and lower speed I/O, and an AMD processor in an AM2 or AM2 Plus socket. In the diagram, we've illustrated an AMD Phenom processor, but this could equally be an Athlon or Sempron processor as well. When AMD acquired ATI, we found ourselves with two distinct streams of semiconductor process technology. There was AMD's traditional SOI technology, where we continue to manufacture our processors at our foundry in Dresden, among other locations. And then there was the ATI model, where we used third-party foundries, largely TSMC and UMC. And the 780G follows that traditional ATI model. It's manufactured at TSMC in their 55 nanometer process, with a little over 200 million transistors, but in a very compact 64 square millimeter die size, and at a core operating voltage of between 1 and 1.1 volts. What you see on the right-hand side is an actual photo of the die. For those in the audience with keener eyesight, you may notice that there's actually some discontinuities in the photo, and that is a function of how the image was gathered. It was actually taken during the manufacturing process at TSMC after the metal 2 layer was applied to better show some of the structures out of a total of 8 metal layers in the chip. And the equipment which TSMC had to photograph the die at this stage during manufacture is not sufficient to capture the entire die surface with one photo. So they took a variety of smaller photos of subregions of the die, and then digitally stitched those together to create the complete image. In terms of the actual logical operation of the chip, this oversimplifies it a little bit, but basically you can think of the product as consisting of 4 major interface areas and then some stuff in between. And in terms of the interfaces, we have a memory controller, HyperTransport, PCI Express, and a variety of display outputs. The memory controller optionally talks to either the local memory, the display cache memory, or directs memory requests to the HyperTransport block, where they can be then forwarded to the system memory, which in AMD's architecture is connected to the processor. So those requests need to go across HyperTransport. The display block, as I noted earlier, incorporates direct support for all of the major outputs that we're required to support, whether those be analog or digital display outputs. And then towards the bottom of the diagram, you'll see a graphics core, which consists of the 2D and 3D engine, and the closely related technology of our UVD, or Unified Video Decoder block, which provides a dedicated acceleration for the decode of HD video content. And right in the center of the diagram, you'll see our bus interface and I/O controller units, which essentially provide the traffic cop function of directing graphics and other requests from the right clients to the right interfaces. So in designing the 780G, although Many people typically think of IGP products as being relatively straightforward, simple, low-cost products. We actually faced a number of very significant design challenges. The first of which was the aggressive schedule requirements that were imposed on us by the market and by our customers. For those of you familiar with the PC market, you'll know that there's several major annual cycles, and mainstream PCs in particular are very much tied to these annual cycles. And maybe the most significant of these is the so-called back-to-school cycle, which one interpretation of is annually having a PC on the shelf at a retail store by the 1st of July. What that means for an ASIC vendor is that we need to have our ASIC in volume production several months before that so that the supply chain can take care of things from there. So we had a fixed market window to hit with a 780G in early 2008 for mass production based on the commitments we had made to our OEM customers. And further complicating things, there were several key new features going into the product which were deemed mandatory by our customers, most notably the DirectX 10 3D graphics capability. We also faced some fairly significant challenges in terms of our power and cost targets. Because it's going into a segment of the PC market which is so cost sensitive, we had no room for compromise on layout efficiency, so we weren't able to take any shortcuts in that area in terms of getting the chip out. And also we had no flexibility to defer key power management features. To meet the needs of our customers and get in all of these features in a cost-effective way, we elected to use a new process technology which we hadn't used previously for any other AMD ATI products. That was TSMC's 55 nanometer process. And we also incorporated new versions of many key IP blocks. And this is in contrast to the traditional IGP approach of incorporating only technologies which had previously been validated elsewhere in other ASICs. Again, because of power, we had to meet all of our speed targets at 1.1 volts. We didn't have the flexibility to elevate the voltage in order to give us a break on some of the key timing paths. And those targets included graphics core operation at 500 megahertz to meet our 3D performance targets, and operation of the HyperTransport and PCI Express blocks at the frequencies defined by the respective protocols. So now to delve into a few of the more specific details of the design. From a graphics point of view, we integrated a DirectX 10 shader model 4 capable 3D engine running at, as I noted, 500 megahertz. This engine was based on what we introduced several months earlier in the ATI Radeon HD 2400 discrete GPU, and that includes 40 what we term stream processing units, which is the basic unit of 3D acceleration in our architecture. We also incorporate the UVD engine to offload the decode of HD video in a variety of different formats, and an ATI Avivo video post-processing engine, which takes the decoded video and then manipulates it to allow it to be rendered on the screen in the highest quality possible manner. So to talk now more about the unified video decoder technology, because this particular version of the UVD was deployed first in the 780G. It had some precursors in other ATI discrete GPU chips, but this particular version was deployed first in the 780G. And it was is a dedicated hardware decoder for all of the compression formats supported by Blu-ray, that is H.264, VC1, and MPEG-2. It's worth noting that while the 780G was in design, it was not clear to us at that point that Blu-ray was going to be the victorious standard in the marketplace. So we had to also take into consideration the requirements of the HD DVD standard, which fortunately was based around the same 3 compression codecs. Now Blu-ray and HD DVD as well permit streams with compressed bit rates of up to 40 megabits per second, which is significantly higher than you would find in traditional DVD content or broadcast HD content. And the UVD block, in addition to providing a very high quality decode experience, also helps to reduce overall system power consumption and indirectly system noise by offloading this work from relatively less efficient general purpose processors, whether that be the CPU or the general purpose portion of the GPU, into dedicated hardware. This diagram shows in a relatively simplified way how data flows through the UVD block. The UVD block itself is a programmable block, and under firmware control can be configured to do the necessary steps to decode either VC1, H.264, or MPEG-2 content. Conceptually, all three of these compression formats use similar approaches to compression, but they all have unique requirements in terms of the specifics of how they encode and decode content. And then once the content is decoded by the UVD block, as I mentioned earlier, a variety of post-processing steps are necessary, deinterlacing, scaling, color space conversion, plane composition, in order to generate a high-quality image which is ultimately rendered on the screen. In terms of the interfaces between the chip and the outside world, there were a variety of new interfaces which went into the 780G, which neither we at AMD actually, and in some cases, nor anyone else in the industry had previously integrated in this class of a device. This was the first product to combine a DisplayPort transmitter with a graphics core. And in fact, that includes discrete GPUs as well. This was the first product although it was an IGP product, it was still the first product in the industry to directly integrate the DisplayPort transmitter functionality. And in terms of IGP products, it was the first implementation of the HyperTransport 3 interface in an IGP product, and the first instantiation of PCI Express Gen 2 in an IGP product. And as you'll note, all of these interfaces are running at in excess of 2.5 gigahertz, so they're all very challenging to implement in such a cost-sensitive and high integration device. From the display point of view, we integrated essentially the same set of display capabilities in the 780G as one would find in a higher-end ATI discrete GPU product. And that includes the traditional analog display output at up to the maximum resolutions that are typically found in the industry, as well as a variety of digital outputs. Notably, we provided DisplayPort support to interface with the new generation of DisplayPort monitors that are appearing on the market at resolutions of up to 2560 by 1600. And supported audio capability over the HDMI interface to fully realize the potential of HDMI as a digital mechanism with one cable to hook up your source device to your CE device, incorporating video and audio over a single cable. We support both support HDCP content protection on both the DisplayPort and HDMI interfaces, which allows premium copyrighted content to be safely transmitted over those interfaces without the risk of piracy or interference. As I'm sure most of you know, in AMD's architecture, HyperTransport is the mechanism that the Phenom or Athlon processor uses to interface to the rest of the system. And we support in the 780G the latest 3.0 version of the HyperTransport specification. That includes, as is traditional for PC chipsets, a 16-bit upstream and 16-bit downstream HyperTransport connection, so-called 16 by 16 connection, as well as a couple of novel features. We also included the CLMC, or Centralized Link Management Control function, which provides the chipset with the intelligence to scale the bandwidth on the HyperTransport interface according to the immediate usage conditions in order to save power, so that we can scale both the link width and the link frequency. And in addition to that, we support all the low power states which are defined in the HT specification. I'll talk a little bit now about power, but before I get into the specifics, I just want to provide a little bit of historical context. This slide shows the last several generations of chipsets that we've done for the AMD platform. On the left-hand side of the chart are a couple of ATI chipsets that ATI did prior to its merger with AMD. And then the 690G chipset, which was the first chipset produced by the combined entity of AMD and ATI, and the 780G chipset. In green, you'll see information on the process technology and transistor count of each of those products. And in the bronze color, you'll see the idle power consumption. So with the 780G, we were able to, despite increasing our transistor count by several fold, to actually reduce the idle power of the chip quite significantly. And obviously, that's a big challenge and one that doesn't come naturally out of the design. So we had to apply a number of fairly advanced techniques in order to achieve that outcome. Several of those include introduction of what we call a deep sleep state for the GPU, which involves reducing the GPU clocks to a very minimal level in cases where there's no graphics acceleration going on, where there's just display refresh or blank screen. We implemented our so-called power shift technology, which allows, on an instantaneous basis under hardware control, 3D engine clock scaling in response to instantaneous load on the 3D engine. As is traditional in ATI chips, we made very aggressive use of clock gating to, again, under hardware control, gate off the clocks to regions of the chip that are not in current use. And we made quite aggressive use of high threshold transistors to reduce the leakage of the chip. As you're probably aware, when you get into the more advanced technologies, the leakage element of power consumption can actually dominate the idle power of the chip. So we were quite aggressive in use of these high VT transistors to minimize that leakage current. From a system architecture perspective, there were some other things that we had to do to ensure that the overall system power remained minimized. And perhaps one of the key innovations in that area is what we call our display cache, which is essentially a single piece of DDR2 or DDR3 system memory attaching directly to the 780G. One of the drawbacks of AMD's HyperTransport processor architecture is that with the system memory attached directly to the processor, integrated graphics processors need to fetch across HyperTransport through the processor out of system memory, even for display refresh or static screen when there's not a lot else going on. And that generates some HyperTransport traffic and prevents the processor from spending the maximum amount of time it might in a very low power state. Now, what we did to sidestep that in the 780G is implement this display cache to allow, in cases where we're in static screen, such as on the presentation notebook right now, the display refresh to occur out of this local memory rather than across HT and out of system memory. And although that doesn't really reduce the power consumption of the 780G chip directly, it has a fairly significant benefit in terms of overall system power. So, to summarize, coming back to my initial point is that the market expectations of PCs and even low-cost PCs are changing in a way that is irrevocable, and they aren't going to change back. Customers really are basing their PC experience more around media-rich usage models and a lot more multitasking. This posed a lot of design challenges for us, and we met these challenges through use of a variety of technologies from across AMD's IP portfolio, consisting of things that came from what we would term AMD Red, the historical ATI group, and AMD Green, the classic AMD group, including a very modern DX10 graphics core, our UVD technology, and a variety of new interfaces. And we applied a combination of more aggressive use of proven design techniques as well as some new design techniques to limit the overall power consumption of the chip. So with that, I think I've completed my presentation, and I believe we've got a couple of minutes for questions. Thank you.
Do we have any questions?
When we have video, we have got to have smooth, fast forward, and playbacks or reverse. What are the limitations on that? Is that the filtering part, or is it the entropy decoding part?
So really the limitations here in terms of fast forward, rewind, or some of the trick playback modes are more in the interaction that we have with the application vendor, the software vendor, whether that be Windows Media Center or CyberLink or InterVideo. So we have a lot of programmability through firmware of the ASIC and an API which we share with these key application vendors that let them take advantage of the acceleration for the trick modes that they might want to implement.
No, my question was, do you have the horsepower to be able to decode smoothly at 2x or 3x the 40 megabit stream?
We do, but that typically wouldn't be done. So I guess in a case of, say, a fast forward mode in a consumer video player, typically what that would do is it would skip some frames in the decoding.
Yeah, that was the point, without skipping. That was my, can you play it smoothly without skipping frames? Like for content creation?
So we could, and I guess the key example there would be if you wanted to decode some content so that could then be re-encoded in an alternative format, transcoding type activities. So that's sort of what you're getting at?
Right.
Yeah.
It's Ando from MyCom. My question is that the HyperTransport 3 connection to the CPU, what good does it do?
What good does it do? Well, I guess from my perspective, as an implementer of the chipset, it is necessary for us to interface to the processor. That is how the processor interfaces to the outside world. More generally, AMD's direct connect architecture has benefits of allowing the system memory to be local to the processor to allow lower latency access to the system memory, and when you get into more scalable systems, allows a number of processors to be attached together in a more elegant way.
Thank you.
I have a pair of less technical questions for you. First of all, would you remind me when this chip is expected to go to market, a chipset expected to go to market or did go to market? And secondly, if I'm not mistaken, ATI has used USMC as a foundry for graphics products in the past. Is this the first graphics product that you're doing at TSMC? Thanks.
So this is a product which we announced at CeBIT earlier this year, which was in early March, and there was essentially immediate product availability from our partners as of then. So if you're itching to examine the product in more detail, you can quite easily walk down the street to Best Buy, Fry's, or order from Newegg and find a fairly wide array of products based on this. In terms of our foundry choice, ATI in the past has worked extensively with both TSMC and UMC. So although this was our first time using this particular process node at TSMC, we've done a range of products there in the past.
Thank you. One more question?
When I look to main boards on market, who does really use display cache?
We have a couple of different variations of the basic 780G technology, notably for desktop PCs and for notebook PCs. So you'll find that a lot of notebook PCs make use of it for its system power saving benefits. And then on the desktop side, some of the relatively slightly more premium desktop motherboards implement the display cache technology because it also has, although I didn't talk about it too much, an attribute of providing increased 3D performance because it makes more memory bandwidth available to the chip.
Okay, thank you, Niles.
Thanks.
And our second presentation for this session is the primary author was Weiwu, who was unfortunately unable to join us. However, we are fortunate that a alternate has been able to make the long trip from China at the last moment, Zuwei Xu, and as soon as he gets wired up here, he'll be ready. Weiwu is a PhD from the University of Southern California, and he's currently a professor and the chief technical officer of the Institute of Computing Technology of the Chinese Academy of Sciences. He's also served as an associate editor of IEEE Transactions on Computers. And it's my pleasure to introduce our speaker.
Forward, backwards.
Okay, thank you. Okay, 1 second. And this is this on?
Just
Okay.
talk.
Just talk. Okay.
You don't need this because you have the wireless.
Okay.
You can walk around.
Okay, I would like to first thank the Hot Chip organizer to give us this opportunity to talk to our international colleagues. And I just noticed that this is the 20th year of Hot Chips. But 20 years ago in China, for the chips, we had something special. The decision maker in China at that time made a decision to not supporting R&D in microprocessor chips. It's probably understandable decision at that time, but a consequence is that our microprocessor R&D started only recently. So today I'll report to you the Godson microprocessor development, especially the Godson-3 microarchitecture. Okay, I'll first give you a very brief overview of the Godson processor series, but I'll focus on the architecture. And we developed the Godson-3 by architecture and physical design as a kind of a combination. And also Godson is our academic name. But we also, this Godson processors also have a commercial name called Nongsun, which is manufactured and marketed by ST Micro. Okay, so why the China decided to support microprocessors now? You know, the decision makers and the funding agencies, and also actually the IT community come to realize that CPU is important. The high performance CPU refers not to very high end, but the above embedded processor CPU chips. Okay, so here are some numbers. For instance, for the demand side, the China's IT is still growing, but the supply side is not so good. So supply lags behind demand in China right now. And the profit margin of a lot of the hardware companies in China are not so good. In fact, some of the companies, they are diversified into restaurants and other more profitable organizations. Right? Okay, but in any event, in recent years, especially starting in 2006 or 2007, the government funding for CPU design has increased quite a lot. Here I listed some of the funding agencies and institutions for our Godson team. Okay, now the most important one, I guess, is this one, which targeted CPU as a long-term, long till 2020. Okay, so till 2020, China's government is committed to support CPU development. Okay, ICT started to develop Godson CPU in 2001. Actually, a little bit before that. So here we have already delivered 4 CPUs. Okay, and basically we tripled the performance for every generation. And here is another figure showing that we are we still lag behind the international partners a lot. But this is exponential. The vertical axis is exponential. But we are doing our best to trying to join the international community. Okay, now here I have some numbers for the 2006 Godson E, which has some performance numbers. Basically, the floating point and the fixed point performance for the SPEC benchmarks are around 500. The processors we are using now in the market right now is Godson-2F. And the main difference is that we reduced the power and we fixed some performance bugs, and we have better support for the memory and the I/O. And now it's in volume production, and we have about 40 or so downstream partners using Godson-2F to develop various kinds of products. Now, the Godson-2 series is for client devices, the main goal. And so here is our roadmap. And currently we have Godson-2E and 2F on the market. We are taping out Godson-2G within a month. So basically we try to use the SOC methodology to integrate more functionalities in the same chip and without increasing power too much. That way to reduce the cost for our partners. And for next year, we'll try to integrate the general purpose CPU core and some GPU function and the north bridge and the south bridge in the same chip. So we can provide our partners some clean design, so they can just add the memory, and so in the board you can have a very clean board. So that's our Godson-2 series development roadmap. Next, I'll talk about the Godson-3. That's the focus of my talk today. And so the architecture feature is, first we try to have a scalable architecture. I'll explain what we mean by scalability later. And also we need some kind of reconfiguration. And also to support applications, we need to have support binary translations at the architecture level. And of course, low power consumption is always a goal. And our target is to have we'll maintain the clock frequency at 1 gigahertz using 65 nanometer technology. Okay, let me explain this, some of this in more detail. So what do we mean by scalable architecture? Our Godson-3 in the next few years will be a chip multiprocessor with many cores, and we'll start with and within the chip we'll have what we call nodes. Each node is a circle here, and it's the detail is shown here. Each node has 4 processor cores and 4 L2 cache modules, and the connections from the 4 directions. Okay, the east, south, west, north, and so on. And so these modules are connected by a 8x8 crossbar switch. And we call this masters. So we have 8 masters and 8 slaves. And we have we have done some evaluation, and we have decided to use this mesh plus crossbar, and we have chosen 8 by 8 crossbar as the proper size. And at all this level, we have globally addressed L2 cache, and the protocol is directly based cache coherence protocol. And another thing is that the data cache and the instruction cache are both recorded in the directory. So this is one way to support binary translation. Okay, now let me give you a little bit more detail about the reconfigurability. Okay, now let's take one node. First, each of we can have 2 types of cores. One is what we call general purpose cores. Is like for instance the Godson-2 core, and another is the multi-purpose core. It's accelerators. Now the general purpose core is similar to the Godson-2 cores that I described before. But the multi-purpose core are used to support some application domains such as biology, bioinformatics, and some other scientific computing area. And now in this multi-purpose core, we can have 8 computational units, and we can have a reconfigurable data path to help speed up the computation. So the peak speed of the general purpose core at 1 gigahertz is 4 gigaflops. Now here is 16 gigaflops. Okay, Okay, and then another thing is that the L2 cache can be configured as an internal RAM, and also the DMA can just go to the internal RAM directly without going through the entire memory hierarchy. So this is to speed up with communication and memory access. And so we have DMA here and HT here, and memory controller here. Wait a second. And another thing is that our DMA engines support prefetch and matrix transposition. Another thing is that each master has 8 address windows to help the it's configurable, program controllable address windows to help with the how the L2 memories and the memories are used. So in fact, this feature can be good for research as well. To figure out how to maintain the memory consistency and how to allocate memory to different processes. Okay, here are some of the details of our general purpose core and the multi-purpose core. So I will not go through to read this out. Okay, now for one, we did some preliminary performance analysis. For instance, with this matrix transposing functionality in the DMA, we can speed up this function by 15 times. Okay. Another thing is for binary translation. Now, our preliminary result is that we can speed up 10 times compared to a software kernel. And the way we did this is by adding some instructions And also, we have hardware support for binary translation, some of the mechanisms. One way I mentioned is that we have both instruction cache and the data cache recorded in the L2 cache directory. And now for the software stack, we have enhanced the MIPS decode and also enhanced the Linux on the MIPS. But we have a process level virtual machine to support application code in the user mode. And also we have system level virtual machines to helpfully support Windows based applications. Okay, and here are some of the initial performance. Our goal is to have eventually reach 80%, so we can have 80% of the native MIPS performance. Right now we are at a 40 to 50% range. We still have a long way to go, but we did see opportunities here. Okay, and another lesson we learned is that you cannot just have architecture. And our institute is different from just universities. You just do basic research and write papers. We also need to develop products to our users. So physical implementation, we found out that is very important. Here I listed some of the highlight of our implementations. For instance, we use tools, but also for critical components and things on the critical path, we also use manual optimization. Okay, and for instance, for the 4-core, which will be taped out soon. This is just one node, and we'll have a 4-core, 4 general purpose core, and the power will be about 10 watts. Okay. And for the 2 cores, we'll have 2 nodes. This will be taped out in 2009. And for our design now, we'll have 4 general purpose cores and 4 multi-purpose cores. Okay. And I would also like to mention one thing that's as our architecture feature here. Let's see. Our cache, L2 cache, the cache coherency protocol, they have some notion of virtual core. That is, besides these physical cores, the interconnection from the 4 directions can also be viewed as a core. So they are also masters. Okay, that's one way we help achieve scalability. Okay, and so here are some examples of physical design and the parameters that we have achieved. That's the register file, the TLB CAM, and here is the HyperTransport driver and the receiver and the PLL, and our jitter is around 20 picoseconds. And the way we do the design is we always have a test chip, and here is an example of the test chip for customer blocks. Okay. So to recap, our design methodology is to use the tools, but with manual improvement for instance, placement routing. And let me give you some more examples, such as the clock tree. Okay, so it's done manually, and it's very regular. So this is, for our experience, this is much better than the tools can produce. Okay. And this is the layout of the 4-core Godson 3. And as you can see, the L2 are still a lot of area. And that's our crossbar here. So what are we going to use for our Godson 3? It's not just used as a PC. We also will use it to develop our high-performance computers. In fact, we are in the process of developing a PetaFLOPS machine, which will use the Godson 3. And hopefully we can have the machine by 2010. And another thing is that we want to develop high-performance computing for the masses, okay? And in fact, we are here now. We already have a teraflops machine using Godson chips, okay? And we try to lower this to finally to the microwave oven size of teraflops machines. Okay. And here are some of the references materials, okay, if you are interested. So to summarize, CPU design now becomes a priority in China. And for Godson 3, we aim at a low power and a scalable architecture. And it will be used to build client-side systems and petaflops machines and teraflops systems for the masses. And I also want to mention that we are a research institute. We are a non-profit organization. So in addition to producing this kind of products and do technical transfer, we also need to contribute to the community. So we want to have more interaction, and we have an open attitude towards collaborations. And for instance, we are going to hopefully contribute to the community a C simulator of Godson chip to help with our especially academia and our students. And hopefully we can do that by the year end or early next year. Okay, I guess I'll stop here. Thank you very much. Okay.
Thank you, Sui. We have time for a few questions.
Oh, you have that.
Go ahead.
Hi, does the multipurpose core have its own instruction set architecture? And if so, is that available online somewhere?
Yeah. Oh, sorry. Yes, but it's, I don't think we have it online yet. But I will pass this back to our team.
Okay. Do you know when it may be available?
Hopefully by the year end.
By year end. Thank you.
Okay.
Hi, Bill Rash from Intel. The block diagram on Godson 3 showed 2 HyperTransport blocks. Is that 2 separate HyperTransport links, and does that therefore imply you're going to do multi-processing or dual processing systems?
The first answer to the first question is yes. Yes. Yeah. And of course, it depends on where you are in the core. But yes, there are 2. And now, whether we are going to do multi-processing, I think we hope to support that, but that also has to do with our system software. I guess my answer to your question is both yes.
Just the follow-on question then, are you using coherent HyperTransport on those links?
You are talking about the HT.
Yes, I am.
Yeah. Right now, we are our current design is use HT 1.0. The current thing is that within the L2 cache and above, that's hardware enforced coherency. But outside of that, the software will have to do that.
Mm-hmm. Okay, thank you.
Okay.
Mariama from Fujitsu. I have two questions. One, could you mention about the chip size of a Godson 3 chip?
Yes, I think I have that. Is that I don't remember the size myself, but can I get back to you later? Yeah, I thought it's on that thing somewhere.
Thank you.
Okay.
And the other question, can you mention about the fab you are using?
Yeah, we are our manufacturer is ST Micro.
Mm-hmm.
Right.
Thank you.
Okay.
One last question.
Mike Bruzzoni with Camp Marketing. How is the Institute implementing the operating system and applications development? Is that in the Institute right now, or are you coordinating with third parties, and can you name any of those third parties?
Yes. We have a core team within our institute. The Godson team, the hardware part is only about 200 people, but we also have about 50 people doing the compiler, and maybe another similar size people doing the system software debugger and the tools and so on. And we also have about 40 partners doing the application and also the hardware products, and they are doing very different new things like how to help the farmers using the TV to do a low cost IT and so on. So yes, we have a core team at ICT and many partners in over the country, and also in some other countries.
Thank you.
Oh, okay. Thank you.
Yeah, our next presenter is Ronak Singhal from Intel. Ronak has a bachelor's and master's degree from Carnegie Mellon University, and he's been working on x86 processors at Intel for more than 11 years. He's currently one of the lead architects of the Nehalem processor.
Okay, thank you, John. So what I wanted to talk about over the next half hour is give you an overview of the Nehalem microarchitecture, which is the next microarchitecture that we're coming out with at Intel. I'll skip all the risk factors and legal stuff. So the agenda for the talk basically is I want to give you an idea of the philosophy we had when designing Nehalem, talk about what were some of the thoughts going through our minds when we were coming up with the features for Nehalem and what really drove us in the direction that we chose. Then talk a little bit about the core itself, the changes we made inside the processor core, talk about the brand new platform that we have with Nehalem, and then talk about some of the unique power management features that we have in there. So just to put in perspective, where does Nehalem fit into the overall set of projects that we have at Intel? We have something that we call our Tick-Tock development model. What that means is that for every manufacturing process, we have two major CPUs, and we're talking here about the x86 CPUs. The first project that we come out with on a manufacturing process is what we call our Tick. So for the 45 nanometer manufacturing process, we came out last year with the Penryn family of processors. Nehalem will be the second of our 45 nanometer processors, what we call a TOC. We'll be following that shortly with a compaction of Nehalem that we're calling Westmere. That'll be another tick. In general, ticks tend to be smaller microarchitecture changes, and they're really focused on getting the manufacturing process out. And then the talks are really focused on a brand new microarchitecture. And in 2010, we'll be coming out with Sandy Bridge, which will be our next big microarchitecture change. And we've already detailed some of the big floating point extensions that we'll have in that microprocessor. So talk a little bit about what is Nehalem. The first thing to keep in mind is Nehalem is not a product. Nehalem is a microarchitecture that is the foundation for a set of products. The products that we build with Nehalem span all the way from very large servers, MP servers, all the way down to small form factor notebooks. So we have a very wide range of power envelopes that we support with Nehalem. Because of that, we needed to make sure it was something that was a very energy efficient and very scalable design. And we'll talk about that. You'll see how that influenced us in terms of, for instance, the power management. The other way that you'll see how it influenced us is just choosing features for the processor itself. In the past, whenever us as architects had really good ideas for a feature, we had to show it increased performance. And if it increased performance, we'd add it to the processor. Now with Nehalem, we had to show it increased performance, and it did it in a very power efficient manner. If it wasn't power efficient, no matter how good of a performance feature, we wouldn't add it. And again, that goes very much to talk about the scalability that we needed to have with this processor. The other thing is, I said that Nehalem will go from servers all the way down to laptops. When we first looked at this, we said, is that trying to do too much? Are you trying to take something that is meant for one market segment and trying to shoehorn it into the other? But I think the thing we realized as we went through the project is there's actually a lot more in common between these segments than we may have first recognized. So for instance, everyone knows servers want high performance, but in terms of what people are using their laptops for, like many of you right now, we want very high performance out of our laptops. The flip side is energy efficiency. Everybody wants high battery life out of their laptop. We know that. From a server side, as data centers become larger and larger and get constrained by space and power, the power is extraordinarily important, the power efficiency. So we saw actually a lot of synergy between these requirements. But we don't want to be taking a part that is really a laptop part and try to call it a server or vice versa. So we want to be able to target each of the market segments with slightly different pieces of silicon. And this is where we talk about the modularity that we have of Nehalem. So we start with the processor core that is common to all the products. But then depending on the market segment, we can aggregate different numbers of cores, and we'll have in the Nehalem family ranging from 2 cores to 8 cores depending on the market segment. And that will be the portion that's above the orange line in this diagram. The portion below the orange line is what we call our uncore. The uncore is what we can differentiate between products. Inside the uncore are things like the glue logic between all of the processors. This is where we'll have the integrated memory controller that we'll talk about in the platform section. So for a different product, I can have a different memory controller supporting different kinds of memory, supporting different kinds of memory bandwidth. We'll talk about our quick path interconnect as well in the platform section. And again, I can have a different number of links, even all the way down to 0 links, depending on the product segment. As well as my last level cache. My cache size will vary with the number of cores that I have, and depending on how many cores I have, I can vary that size. So we have a lot of different knobs in our uncore that allow us to target each of the products for a market segment, right? So that we're not trying to take a laptop part and put into a server or vice versa. So the first product we'll be coming out with based on the Nehalem microarchitecture is now called the Intel Core i7 processor. This will be a high-end desktop product that will go into production in the 4th quarter of this year. It is a 4-core product with an 8 megabyte last level cache. We'll talk about some of the other features such as simultaneous multi-threading and some of the new instructions in a second, as well as the platform features, specifically the integrated DDR3 memory controller. So the first thing I want to talk about are some of the features we've added inside the CPU core itself. So again, the core is common to all of the products based on the Nehalem family. So regardless of your server or laptop, you have these features. And again, these features were chosen, 1, based on their power efficiency, and 2, one of the other key philosophies we had with Nehalem is that, over time you've seen us go 1 core to 2 core to 4 core pretty quickly. With Nehalem, we had the choice do we continue to go up that increase in core count and provide that as the way to increase performance? Or do we do something more about increasing the performance per core? And our philosophy right now is that per core performance matters. Simply aggregating more and more cores is not sufficient for providing performance to our customers. And a lot of our customers have told us per core performance, or single threaded performance in fact, matters a lot. And so you'll see we spend a lot of effort in improving the performance of a core. Now, of course, this also helps multi-core performance because you're raising the ability of each of the cores as well. So in the middle of this diagram is a picture of the core itself with the major blocks labeled. And around the edges, what you see are some of the key features that we've added for performance inside Nehalem. And so in the next few minutes, I'll talk about a couple of these features. First thing to do is just show a rough picture of the block diagram of the execution units on Nehalem. This block diagram looks very similar to our prior generations, the Marome and Penryn products. In terms of the execution units, we can dispatch up to 6 operations per cycle, which is the same as our prior generations. Of those 6 operations, 3 are what I call computation type of operations. You can see those labeled on port 0, 1, and 5 in this diagram. And we can do 3 what I'll call memory operations, 1 load and 1 store operation per cycle, and those are ports 2, 3, and 4. The major changes versus the prior generations, on port 5, for instance, some of the shuffle hardware. So we have some additional execution units. In the grand scheme of the benefits of Nehalem, these are small. They help clean up the performance on some pieces of code, but they aren't probably a first order performance impact overall. The places where we really see the big performance gains from Nehalem from the core are some of these features here. Just like I was saying, for a large part, you can look at Nehalem as being based on the foundation of the Marome and Penryn, the core microarchitecture. The key things with that are it's a 4-wide machine. 4-wide meaning that the maximum sustainable rate through the processor is 4 instructions per clock. Now you saw in the previous diagram, we can actually execute up to 6 operations per clock, but you can only sustain a rate of up to 4 because the thing going into that execution unit and the thing coming out is really constrained to 4. So it's a 4-wide machine, and then we have, again, starting with the base features of that Marome microarchitecture. So what are some of the key things that we've done inside Nehalem? First, you'll see with every generation of processor, we tend to try to improve the branch prediction accuracy of the processor. Every time we start a project, we look at what are the biggest levers for performance that we have. And inevitably, branch prediction continues to be one of the biggest levers. As our cores get faster and faster, the ability to improve or predict your branches correctly is important, right? Because each time you take a branch misprediction, you have to flush your pipeline and so forth, you're paying a high opportunity cost. So with Nehalem, we have 2 significant changes with the branch predictor. The first one is we add what we call our second level branch predictor. It's basically a branch predictor focused on capturing applications with large code sizes and capturing the branches in there. So the classic example that we use for that is large database applications. The second change we've made in our branch predictors that's significant on Nehalem is something that we call our renamed return stack buffer. In x86, call and return instructions are used to enter into and return from functions. And typically, x86s use a return stack buffer to predict those return instructions. In the past, our RSB, our return stack buffer, could be corrupted due to other mispredictions occurring between the call and the return. With Nehalem, we now rename the return stack buffer like we rename other resources in the machine, so we can basically eliminate all of the return mispredicts. A second substantial change that we've made to Nehalem is how do we extract more parallelism from the hardware, from existing software by the hardware? If you attended yesterday's panel discussion, I think Nathan said one of the worst, I don't know what the exact wording was, one of the worst ideas or one of the most misguided ideas was instruction level parallelism. And I'm surprised nobody took him to task for that. We still believe instruction level parallelism is very important. And so what you see here with Nehalem is we've increased the size of our out of order window by 33% on Nehalem. What that means is that the hardware can look at up to 128 operations at a time, trying to find independent operations to execute on. So if I have a cache miss, I can still be doing a lot of work underneath that. So how do I find more and more independent operations to keep my powerful execution engine busy? And when we increase the size of that out of order window, we have to increase the size of other structures along the way in the processor so that they don't become the bottleneck. So you'll see, for instance, that our scheduler is deeper. You'll see that we can support more cache misses in flight than our prior generation. So each of these adds to the ability for the processor to find more performance through added parallelism. And then finally, another set of improvements we've made is around the memory subsystem itself. One thing we've done is something called fast 16-byte unaligned accesses. In fact, one of the media presentations yesterday talked about why fast unaligned accesses are very important for a lot of media algorithms. And this is something that we see as well on applications that people care about the performance on, is that the compiler or the software writer can't always guarantee the alignment of a piece of data with regards to either a 16-byte boundary or a 64-byte boundary, which is our cache boundary. So we want to make sure not to penalize the programmer in those cases. And so we have this new 16-byte fast unaligned access to do that. And this is not new code, it's just making existing legacy code faster. We also moved to a second level TLB scheme. So now instead of having just a first level instruction TLB and a first level data TLB, we have a second level TLB. It's a unified TLB, both instruction and data, 512 entries in size. As applications data size grows larger and larger, we see the TLB performance becomes a larger and larger effect. And then finally, we're asking people to thread their programs more and more. As we're doing that, we want to make sure that the synchronization between threads does not become a bottleneck. And so one of the things that we've tried to do is reduce the cost of the synchronization primitives in x86. And so you can see that that's the graph at the bottom of this slide that shows that over the past few generations, going from Pentium 4 to the Merome family, we significantly reduced the latency of those locking operations, and we take a similar reduction with Nehalem, going from Merome to Nehalem. So in general, there are a couple things to note from all of these features that I just talked about. The first thing is that they're really targeted at helping legacy performance, meaning they're not requiring new optimizations, they're not requiring new instructions to be used or new compilation. Our first and foremost performance target is all the code that's been written already. You know, one of the Nehalem architects is very fond of saying that 95% of all the code that will ever run on Nehalem has already been written today, before Nehalem ever exists as a product. And what that really means is that for people to get performance out of Nehalem, we don't want to go to them and say, you have to go recompile, because for a lot of people, they just simply won't do that, right? So we want to focus our performance features for a large extent on features where people will get the benefit out of the box. Now, that's not to say you can't optimize for Nehalem. You absolutely can, and there are performance benefits to be had by either recompiling or taking advantage of some of the other features we'll talk about in a bit. But that's our general philosophy, is that's the priority. Next, I want to talk about the cache hierarchy. It's now a 3-level cache hierarchy. In the past, we've only used 3-level cache hierarchies on our server products. This will be the first time that we have a 3-level hierarchy going all the way down to our laptop and desktop products. The first level of the cache hierarchy is similar to what we have in the Core 2 family, 32K instruction cache and a 32K data cache. The second level cache is private to each core as well. It's a 256K cache, holds both instructions and data, and it's designed to have very low latency. It's a 10-cycle load-to-use latency on our second level cache. The reason to have the second level cache is because of our new third level cache. The third level is shared across all the cores. No matter how many cores we have, whether it's 2 cores, 4 cores, or 8 cores, the third level cache is shared across all those cores. What that means is that a single core can use the entire cache. The size depends on the number of cores, and like you already saw, the initial quad-core product that will be based on Nehalem is an 8 megabyte cache. And one of the key aspects of our third level cache on Nehalem is that it's an inclusive cache. What we mean by being an inclusive cache is that any line that is present in the L1 or L2 of a core must also be present in our L3. And the reason we do this is it basically gives us a very nice snoop filter capability, so that as we add more and more cores and they have to access the third level cache, they don't increase the snoop traffic to each of the underlying cores. Or as we add more and more sockets in a multiprocessor system, again, the additional snoops to the third level cache don't perturb your cores. So we get very nice snoop filter behavior from our third level cache. Just very quickly, a couple of other key features we have on Nehalem. We do have a handful of new instructions. We have 7 new instructions called SSD 4.2. 4 of them are targeted at accelerating the processing of string and text in XML. We also have a CRC 32 instruction for accelerating the computation of a CRC for the iSCSI networking protocol. We've also seen people use this in a more general form for doing fast hashing. And then we have a pop count instruction for counting the number of ones in a register. In terms of virtualization, we also are going after virtualization performance quite aggressively. First and foremost, though, to get the best virtualized performance, we really believe you have to have the best native performance, and then you build up from there. Once you focus on the native performance, then the two things to go after are, one, how do I reduce the number of times that I have to exit from my virtual machine back to the host? And secondly, when I do have to exit, how do I minimize the latency of those transitions going from the guest to the host and back? And so we have changes at both the microarchitecture level in reducing the latency of those transitions. And again, that's shown on the graph on this slide, bringing down that latency with each successive generation. And then we have architectural changes, such as the new extended page table functionality, to reduce the number of times we actually have to exit out of the virtual machine. Since I'm running a little short on time, I won't go into that in detail, but if you have questions, we can talk about that later. Wanted to briefly touch on simultaneous multi-threading or hyper-threading technology. This is the ability for the hardware to run two software threads simultaneously in the hardware. So it's really the case that they're simultaneous is one thing to take away. I showed that block diagram earlier. SMT really means that one of the adders can be doing an add from one thread while the other adder can be doing an add from the other thread. It's not the case that we switch in one thread based on the behavior of the other thread. They're really executing simultaneously. The two main reasons we really like SMT are, one, we talked about this very powerful execution engine where we can handle up to a maximum throughput of 4 instructions per clock. But the fact is that there's very little software in the world that can hit that 4 instruction per clock limit. SMT gives us the ability to come closer to that limit by overlaying 2 software threads at the same time. The second thing that SMT does is the most power efficient performance feature that we know of. I'll show you some performance numbers in a second, but in the cases that we get performance out of SMT, the reason that it's very power efficient is we've spent very little die area. The whole concept of SMT to us is take advantage of the resources you already have in the machine, use them for that second software thread, add the minimal amount of hardware needed to manage that second thread, and see what performance gains you get out of it. So we get very good performance in many cases for a very small area of die cost, and die cost translates directly to power. So here's an example of some of the performance numbers we've measured so far on the i7. So these are focused on desktop kind of applications. What is the impact of turning on the SMT or the hyper-threading capability versus not having it on a Nehalem? So you can see standard benchmarks like SPEC-FP, which is the floating point, or SPEC-int rate, which is the integer one here, showing 7 and 13% improvements. Over 30% on something like the new 3D Mark Vantage, which is a gaming CPU test. So things that are threaded, applications that are threaded, we can show significant performance benefits from the SMT implementation that we have on Nehalem. So now briefly we want to talk about the new platform architecture that we have with Nehalem. The big thing is that over the past decade, with our x86 CPUs, we've been using a front-side bus as our way to connect to memory. And those are, various forms of that are shown here. With Nehalem, the front-side bus is gone, and instead we've moved to a new platform architecture. So what I'm showing in this diagram is what the server, or two-socket server platform will now look like. The first thing you'll notice in orange is the new integrated memory controller. So the DRAM will be hanging directly off of the CPU. In our first products, including the i7, it's a 3-channel native DDR3 memory controller. So it's designed for very high bandwidth, and we'll show some bandwidth numbers in a second, and very low memory latency. The other key part of the new platform is shown in black, and this is the new Quick Path Interconnect. It's a new point-to-point interconnect that we'll use to connect between sockets of a CPU, as well as to connect the CPUs to our chipset, labeled here the Tylersburg chipset, which is really our I/O hub. And we'll offer that Quick Path Interconnect at various speeds. In the first implementation, it'll be up to speeds of 6.4 gigatransfers per second. That translates into 25.6 gigabytes per second per link. In terms of the memory bandwidth that we get from our memory controller, like I said, it's a native DDR3 memory controller, and it's 3 channels per socket on the first implementations. So the graph here is showing the memory bandwidth we can measure today using 1066 memory with Nehalem. We're getting over 33 gigabytes per second in a 2-socket system. You compare that to the best Xeon, the best two-socket x86 we have today, where we get just under 10 gigabytes per second. It's a massive increase in memory bandwidth. And so when you look at applications like high-performance computing applications, there's a significant performance boost that Nehalem gets as a result of this new platform. The other part of the new platform that's important, though, is what is the impact on memory latency. By bringing the memory controller on die, by moving to native memory, we're able to reduce our memory latency versus our current Xeon products. What this chart is showing at the bottom is that in yellow, that's our current memory latency with today's Xeon products. The middle bar talks about what is the latency for a CPU to access the memory that is hanging off of its socket. And you can see we get about a 40% reduction in memory latency with Nehalem. Now the other thing is, if you remember that platform diagram on the previous slide, or 2 slides ago, there's now memory hanging off of each CPU socket. So it's possible that one CPU has to go over to the other memory to fetch it, what we call a remote memory access. On this graph, you can see that the latency of a remote memory access is slightly slower than the latency of today's Xeon. So regardless of the mix of local and remote memory accesses on Nehalem, you'll come out with an overall better memory latency. And obviously, if you apply NUMA optimizations and try to be in that local space for the majority of memory transactions, you'll get best performance. So that's the really quick overview of the brand new platform that we have in Nehalem. The last thing I want to talk about is some of the unique power management features that we have. One of the first things that we've done is add something that we call our power control unit. What the PCU is a microcontroller that is now sitting inside our Uncore and is used to really control the power management of the processor. In addition to that, we have sensors for determining the temperature, the current, and the power as well. And why all of this is beneficial to us is something we'll talk about in a second that we call turbo mode. But before we get to turbo mode, there's one other key innovation that we have in Nehalem around power management, and that's something that we call our integrated power gate. The power gate, you can really think of this quite simply as a very large transistor that sits between the cores and our power supply, or the voltage regulator. And so if a core wants to go to an idle state, or to what we call a very low power state, a very low C state, which the OS will tell the processor to do, we will actually be able to cut the power to that core so that it's not even leaking. So basically the power consumption of that core is nearly zero. By doing this, this gives us the ability, one, to have very low idle power on this processor. And the second thing is, if I'm only running several cores, let's say I have a single-threaded application or a dual-threaded application, I can run those cores at a high frequency and have the other cores turned off. And the way I take advantage of that is with turbo mode. So for the example I just gave, we have 2 cores running. The other 2 cores are shut off through the use of the power gate. I now am able to detect with those sensors I have how much power am I using, how much current am I using, what temperature I'm at. If I'm within the limits of the processor itself, I can increase the frequency on those cores. And this is all done through that power control unit that I just described. We'll effectively increase that frequency so that the cores that are running, that want performance, can get higher performance, but I'm still doing it within the power envelope of my product. I'm not exceeding that. And again, by having the power gate so that the cores that aren't being used aren't leaking, I get a benefit. Now, the other thing about turbo mode is that I can get the benefit of turbo mode even if all 4 cores are running. So it's not the case that cores have to be idle to get the benefit of turbo mode. It's just that the benefit varies depending on how many cores are active. So this final case shows that if there's just a single core active, I can potentially get even more frequency. The key thing with turbo mode is the amount of the gain that you can get from it really depends on how many cores you have and in what power envelope you'll be in. So you'll see that the first Nehalem products, which will be the quad-core high-end desktop products, will come in a very large power envelope, 130-watt power envelope. And so we're not that power constrained. So the benefit from turbo mode will tend to be what I'll call modest. When we get to future Nehalem products, such as quad cores and much smaller form factors, and we are much more power constrained, the benefit from turbo, the potential of that benefit, will be much, much more significant. So really, this is a technology that's setting us up for much higher performance as we increase our core count, but we don't want to penalize people for running low-threaded applications on our processors. So in summary, that's the really quick overview of the Nehalem microarchitecture. It's our second 45 nanometer product. We have talked about power efficiency, scalability, and performance around the core, the platform, and the power management. So with that, I'll take questions.
Ando from Micom.
Go ahead.
Go ahead.
Regarding the power gate, may I ask the die area overhead and the delay overhead?
The die area, I don't know off the top of my head. The delay, what do you mean by that?
The power gate transistor inevitably reduces the supply voltage slightly, so the gate would go slower.
I'm still not. Oh, droop, not drop. Oh, the voltage drop, I see.
Through the power gate.
Yeah. Again, that's not a number I know off the top of my head. Sorry.
Two questions about the power gating. For the, let's see, so you mentioned about the fast voltage ramp, and how much time delay are you talking about? Is that 10 microsecond or how much?
Between what 2 points?
I'm sorry?
Time delay between what two, starting when, ending when?
Yeah. After the power gating and ramp up the power to the operational mode.
So the best way to talk about it is what do we think is the performance impact of if a core has to go, if we turn it off and then turn it back on. And we believe that everything we've shown so far shows that it's negligible in most cases.
Okay. The second question is for the power switch, how these PMOS switch is distributed over the core? Is that
each core has its own switch.
Yeah, but is that just surrounding those switches is just surrounding the periphery of the core, or more distributed inside the core?
You'll have a switch basically at the edge of each of the cores to do that. Now within the core, we'll still have all the usual power management stuff like clock gating and so forth for much finer grained power management. Right?
Just to confirm, those power switches are periphery, placed in the periphery of the core. Is that correct?
Of the core, but kind of between the core and the uncore. Yeah.
Thanks.
Lennox High HP. Just a quick comment. Both the turbo mode as well as the previous one, the power shift. If you do a Google search, it came out in 1993 concept. So.
Well, there's a difference between concept and reality in a high volume product, right?
I agree, but there are some historical notes need to be noted.
That's fine. Nathan.
Yes, I'd like to clarify my comments from last. When I was panning instruction level parallelism, it was the explicit instruction level parallelism that one has to mine at compile time, as opposed to the ILP that you can get on the fly through clever reordering and issue and all the rest of that.
Good clarification.
But a question for you, is the inclusive structure of the cache also applied to the L2s and L1s?
No. So the L3 is inclusive of the L2 and the L1. The L1 and L2 have no relationship to each other. They're neither exclusive nor inclusive.
So basically, then I need, in an 8-core system, 2.5 megabytes just to cover the L1s and the L2s in the L3. Is that correct?
In an 8, that math sounds about right.
Okay.
Yeah.
Thank you.
Last question.
Hi, Derek Mihuchka, emulators.com. So I seem to recall that one of the problems with the original hyperthreading that came out in the Pentium 4 was that the operating systems at the time, like Windows XP, just were really tuned for multi-socket SMP, and so they just did round-robin scheduling because they didn't really treat different threads as having kind of different costs or different advantages. And so, for example, I can see with this ability to turn off cores or this overclocking, if you have an operating system, if you're telling your computer, let's say, run in a performance mode, you would want the OS to schedule 2 threads on separate cores. But if you're in a like a battery saving mode, you would want to turn off the cores and schedule 2 threads on 2 hyperthreads. And I don't think Windows or maybe even Linux has the smarts for that. So
you're right about that. So that's more of an area of research, because just like you mentioned, a lot of people have said, hey, we can schedule for power as well as schedule for performance. They're not doing that as of yet.
Right. So let's say when this chip comes out in a few months and I'm running Windows Vista, is Intel working with Microsoft to make sure that, say, the Windows 7 beta will have these smarts, or is this something that hypervisors are? Can the turning off of cores be done, say, programmatically, so that a virtual machine hypervisor could actually do this kind of scheduling?
So the answer to your question is both the OS or the hypervisor can manage where threads get scheduled. So either of them could be able to do that. Right? We are talking, you can imagine, with Microsoft and all the other OS companies about what's the best policy for both performance and for power, and doing experiments along those lines.
The actual the gating of the cores where you shut the power off.
And that just uses the existing power management hooks that both OSs today use and some of the hypervisors use.
Okay.
Let's thank Ronak and all our speakers this morning.